multi-threading models. Fine. So all of you know that user programs are being executed, and user program takes the help of OS services, which is in the kernel mode. Okay. Now I have told that any program which is under execution is nothing but a thread which is under execution. Any program is a thread. Okay. So when this program is executing, it should get connected with the kernel thread to, which is also a thread in the operating system mode. So whether it is an operating system or a user level program, it is the threads which is executing in the system. Okay, so the operating system, it should get connected with the operating system thread. Again, it's a program. Thread is nothing but a number of threads. If it is a multi-threaded program, number of threads make that particular program. If it is a single threaded program, a single thread makes that program, makes a particular program. Fine. So there are different threading models, different ways in which the connection can take place. Many to one model, one to one, and many to many. Okay, important question again here. Multi-threading models. Okay, so 3 types of multi-threading models: many to one, one to one, and many to many. Okay, we'll see what is many to one model. Fine. So in many to one model, there are many user level threads and only one kernel level thread. That's it. Very easy. Many user level threads and one kernel level thread. So it can be of the same process again, or it can be of different processes. Okay. So different processes or same process. So this is a multi-threaded program. Fine. So all these user level threads are accessing this only one kernel thread for all its requests. Okay, so P3 program, so this particular thread wants to take the help of the printf, means it wants to take the access the monitor. It sends a request to this kernel thread. Okay, so P1 program wants to access the memory. It sends a request to the kernel thread. All is handled by the single kernel thread. Okay, that is many to one model. So all the thread libraries. Okay, there are thread libraries in the user space. So this the thread libraries takes care of this user threads. Okay, so many user level threads are mapped to single kernel level thread. The only disadvantage is this. The only disadvantage is if a thread gets blocked. Okay, that is, if a thread gets into a block state here, and that is due to an infinite function, it gets blocked, the other programs, other processes, and other threads will not be able to continue the execution because the kernel is not free. It is blocked into an infinite state here. Okay, and this is again resolved by the thread libraries. We'll see that later. So this is the disadvantage of many to one model. Fine, it will get blocked if one thread, okay, the entire process, all the threads or the entire program, all the programs will get blocked with the if there is as there is only one single kernel thread. Okay, this is so one thread can access a kernel thread at a time. Only one thread can access kernel thread at a time, and it is used in some rare operating systems like Solaris Green Threads operating system. This many to one model is used, or the portable threads, GNU portable threads. Okay, so a part of operating system of the Linux. So GNU portable threads, this system technique is used of creating many user threads and only a single kernel thread. Okay, so what is the disadvantage? If the a single thread gets blocked, okay, uh, if it is gets into an infinite loop here, then till it's unblocking, the other threads cannot execute further. Okay, next is one-to-one model. In one-to-one model, as you can assume, there is only one user thread which is connected with one single thread. Okay, all single user threads, many number of user threads, are connected with many number of kernel threads. Okay, there is user thread and its kernel thread. Fine, user and its kernel thread. Okay, so all has its own kernel threads, no blocking here, because even if one user thread gets blocked, there are other kernel threads and other user threads which can keep on executing. It runs, it doesn't stop the execution of other user threads. Okay, so user threads are where user programs or application programs are running, which is returned by the developers for some specific task. Okay, so what can be the disadvantage of this model? Okay, fine. Advantages: it can make use of the multi-core architecture, as it is not getting blocked, and each user thread has its own kernel thread. Any request for the user thread, there is a particular kernel thread to serve it. Whereas in many to one, okay, many to one, there is only one kernel thread. Okay, so it cannot use of multi-core architecture, because only the user level threads to some extent can use this multi-core. Okay, but usually for every nanosecond there is a need of the kernel, that is operating system. Fine, that is accessing the memory, accessing the processor, accessing the virtual memory, taking the addresses. Okay, for all this the operating system services required. So as there is only one kernel thread, a multi-core architecture could not be used in many to one model. Okay, many to one model, whereas here one to one model, multi-core architecture can be used. Disadvantage: what is the disadvantages? It is slows down the system, because as many user threads are there, that many kernel threads must also be created. Okay, much space is occupied. Fine, so as there is no restriction on the number of kernel threads which is created, one user thread is created, immediately its kernel thread is also created. Okay, so much space is occupied, and these threads has to be managed also, so it is an overhead, it is a issue which has to be handled. Okay, so it is used in Windows NT, Linux, Solaris 9, okay, and later systems. So faster execution, but as the number of user threads increases, there is restriction in the number of um, mm, as the number of user threads increases, the system slows down. Okay, as there is no limit on the number of threads which is created. Okay, there is no limitation. A program is executing, it can create its own number of user level threads, and correspondingly its kernel level threads are also created. Okay, so you can note down the examples of operating system which uses the threads. It is Windows NT, XP 2000, Linux, Solaris 9, and later systems. Next model is many to many model. So as you can expect, so many user threads which is connected with many kernel threads. Always the kernel threads which is created will be only if required. Okay, that is the how many of user threads are there, less than that the kernel threads will be there. It is Not like one user thread is created, immediately kernel thread is created. Not like that. Only when it is needed, the kernel thread is created. And always it will be less than the number of user threads. Okay. So it is many user threads mapped to many kernel threads. It is less than or equal to the number of the user threads. Okay, so the kernel threads will be less than or equal to the number of user threads which is created. Okay, I think a wrong statement here. Does it means that, okay, lesser or equal number of kernel threads, lesser or equal than the user threads. Fine. So overcome the disadvantages of both the previous models. What was the disadvantage of previous models? Many to one. What was the disadvantage? In many to one model, the blocking was happening. Okay, so here, even if one thread gets blocked with one of the kernel thread, there are other kernel threads to serve the other processes, other threads. Okay, so the disadvantage of many to one model is overcome, and the other disadvantage of the next module, that is one to one model, disadvantage was many number of kernel threads. As many user threads, that many kernel threads were created. Here that problem is also solved. How is that? Only if required, the kernel threads are created, and it will be always less than or equal to the number of user threads. Okay, it is always less than. Okay. In this diagram also you can see it is less than the number of user threads. Fine. So these are the examples. In a version of Unix operating system and Solaris 8 and earlier systems, this technique was used of mapping. Okay, so you have seen in this class three models of multi-threaded mapping. And the next topic is, so there are some issues when the threads are used in the programming. Okay, so it is not like usual process what you have seen till now. Okay, it is not a process, it is a thread. So what are the changes in the usual things what you can see? What are the changes with the programming when threads are used? Issues to be handled when threads are used. Okay, or how does the thread work? So that is this topic. Next, so first is the use of fork and exec. So this is a thread which is executing. Okay, so this is a thread which is executing, and in this thread I use fork. So what happens? What happens when a fork is called? A new process is created. Correct? New process is created. So it is the new process of this particular thread, that is a copy of the thread is created, or a copy of the complete process is created, program is created. So there are some issues which has to be handled. And what is exec? We will see thread cancellation. You have seen process cancellation, how a process is cancelled. Okay, cascading cancellation, that is whenever the particular process is not required by the parent process can terminate the child processes. Okay, you have seen that when are the conditions when the child process can be terminated. So how can the thread be terminated, cancelled? That we'll see. And signal handling, what happens in signal handling? What is the thread pool, thread specific data, scheduler activation? All this is the next topic, threading issues. Okay, fine. We'll see at least two contents out of this. It is fork or exec system call and thread cancellation. So what happens when a fork is called? As I told, a thread is invoking the fork system call. It is not the process. Okay, a single thread is invoking the fork system call. Fork means it has to create another process. So the main issues here, there are two things what an operating system can do is, whenever fork is called by a thread, a process is created. Yes, a new process has to get created. So the new process which is created can be a copy of the whole process, whole program with all number of threads. If there are 50 threads, all 50 threads will be a copy of this new process, or it can be a copy of the single thread. Okay, so that is the two options depending on the design of operating system, how the whenever a thread is calls this fork system call, how it has to be handled, how the memory has to be divided, and how the copy means if fork is called, a new process is created, how the new process must be. It can contain only the calling thread, a copy of the calling thread, or it can be a copy of the whole process with all the threads created in it. Okay, so that is a fork system call when a thread calls. What about exec? You know that exec, when it is called after fork, what happens? It executes the task which is assigned by the exec. Suppose fork creates a thread. Now I use exec here. I had told this earlier. So exec, whatever function is passed here, whatever program is passed as a parameter here, okay, program1.c. I'm just giving an example. So here program1.c has to get executed by this process which is created using fork system call. Okay, so exec is always called immediately after the fork function is called. Fine. Fork function, what happens? New process is created. What that new process should do, it is mentioned here in exec system call. Okay, so when the exec system call, it tells which function has to be executed by this particular, what task has to be done by this particular child process, which is created by fork system call. Fine. So that is how the fork is handled in threads. Next we'll see about the thread cancellation. Yes.
Ma'am, why is that fork and executing system call? Why are there issues, ma'am?
Why are the issues? Okay, so what happens when the usually when in a program, suppose it is not multi-threading, okay, in a single threaded program, fork is called. Okay, so we have studied this. What happens whenever a fork is called, it is a copy of the same parent which is given to the child process. Okay, child process will be a copy of parent. Okay, now when the fork is called by a thread, which is the parent of the fork? The parent of the fork is this thread. The parent of this new process is this thread. Okay, it is not a process. This is a process P1. When fork is called by process P1, a copy of the process parent process is created. Okay, so here a copy of this thread has to be created, or a copy of this process has to be created. So two issues here. Okay, it can be done in two ways. Fork system call. Fine. So the issue is, usually when we say fork is it creates another process, and the new process which is created is a copy of the parent process. Okay, so here when a process, when a single threaded program is calling this particular fork system call, a copy of this whole process is created. Okay, now who's the parent of this particular new process which is created? That is the issue. Whose copy it should be? It should be a copy of this single thread. Okay, that means how the thread, how the program will be. Okay, so how the program will be is, now this is the thread T3 which has invoked the fork system call. The new child process which is created can be only this thread T3. Okay, or it can be with all the threads T1, T2, T3, and this is the new child process which is created. So two ways in which the process can be there. Fine. So that is the issue here. It is not the same way in which where a single threaded program and the fork system call is called. It is not the same way which it has to be handled. Okay, it can be handled in two ways, whether it can be a copy of the single thread or it can be a copy of this multiple thread. The new process which is created can, this is the new child, or this can be the new child. Okay, and this issue must be decided when the operating system is designed